presentation is Power Equipment Management, Part 1, Fundamentals. Okay.
Good afternoon. A brief introduction of myself. My name is Qiu Gang. I'm a senior engineer at the Research Institute of State-Grid Jiangsu Electric Power Corporation, which is a subsidiary of the State-Grid Corporation of China. I'm very honored to stand here and share with you our latest research progress of standards in action of power industry. Since this is the last presentation, I will make it quick. As we all know, on April 28th of this year, the entire electricity power network of Spain and Portugal experienced a blackout, with the exception of islands that operate on separate grids. Both nations, along with some regions of southern France linked to the Iberian network, were left in darkness. This incident stands as one of the most significant power outage in the history of European countries. Currently, the exact causes of this event are still being investigated. Is this the only large-scale blackout we have encountered? The answer is no. I inquired with ChatGPT and DeepSeek to gather historic data on the top 10 significant power outages. The findings are listed on the left. From what we observe, large-scale power interruptions are likely to occur every few years. Many of the historical incidents were mainly caused by environmental or meteorological factors. This brings us to the question, why does power outage occur? Despite all the advantages in the design, installation, and management of power grids, failures in power grids are unavoidable. From the perspective of experts in power industry, power outage occurs due to two main reasons. First, the complexity of the power grid. Modern power systems consist of intricate networks involving generation, transmission, and distribution. Even a single fault can disrupt stability. Second, the challenge of balance difficulty. Electricity supply and demand must match real-time. Electricity supply must precisely match real-time consumption, because electricity cannot be restored. Any imbalance will lead to the blackout. In this case, all electrical components, including transmission lines or transformers, play a critical role in the system. Failures in this system may trigger a cascading effect that can compromise the entire grid. To enhance their operational data stability, it's essential to implement geographically information strategies. In the past, fundamental and essential documents regarding power construction material were often stored and managed on paper. However, the reliability of this construction data has gradually diminished as time goes by. In the meantime, there are no effective methods for monitoring the operational stature of these power facilities, especially those located in the remote area. Maintenance team can only rely on visual inspections to assess the condition of the facilities. What activities are grid operators currently doing? Let's consider the state grid of China as an example. As the largest grid operator in the country or even in the world, SGCC served a population of more than 1.1 billion people over 26 provinces. The State Grid Corporation of China boasting over 1.2 million kilometers of transmission lines and 30,000 substations encounter significant challenges in managing and operating such an extensive power network. In order to effectively monitor the operational condition of equipment distributed throughout the country, the company utilized a network of sensor devices. This includes on-site cameras, current sensors, weather monitoring device, and fault detection devices. These technologies enable real-time supervision and management of the infrastructure. Moreover, power grid operators make extensive use of cutting-edge technologies, including drones and robots, to capture high-resolution images and perform laser scan of the electrical infrastructures. This development facilitates the use of drones to inspect transmission lines, which is crucial for monitoring the distance between power lines and the nearby vegetation. Insufficient clearance may lead to failures in transmission lines. Additionally, the 3D model of the transmission line generated from laser point cloud data contribute to various applications. It's foreseeable that the electric power operators who owns a lot of power facilities and an increasing number of sensors is now faced with the new tasks of how to effectively utilize this data. Considering the advantageous spatial attributability of the power infrastructure, we have developed a geospatial tool called Power Map. This map integrates static grid information, real-time operation data, and weather-related data into a unified system. As we can see, the Power Map illustrates the locations of transmission lines and substations, organized according to various voltage levels. It features areas of interest that are color-coded to represent different land covers identified through an AI process. For instance, in certain circumstances, tall trees and greenhouse film identified as potential hazards are emphasized to indicate the risk to the operations of transmission lines. Experts utilize this map to enhance workflow efficiently. It's clear that the popularity of this map depends on the accuracy of the fundamental grid data, which consists of static and dynamic operational data sets. A crucial element within this data is the grid equipment ladder, which contains geospatial coordinates and other things for the infrastructure. However, as mentioned above, years of grid development have led to issues such as overlapping information layers, inaccurate records, and incomplete historical data set. This has made traditional manual information management technologies inadequate. These two pictures demonstrates the application of satellite remote sensing imagery and AI-based models to rectify inaccuracy of the transmission line records. For instance, it was discovered that the actual location of certain transmission towers differed by more than 100 meters from the information recorded in existing data. After implementing tolerated corrections for more than 200,000 transmission towers throughout Jiangsu province, significant improvement in the data accuracy and operational efficiency has been achieved. Besides this, compared to traditional thermal power generation method, innovative ways of power generation, such as photovoltaic systems, have emerged as a focal point in power industry. The integrated use of photographic information has enabled the assessment of potential and the planning of a construction for rooftop solar panels. People around the world are encouraged to install solar panels on their roofs and sell electricity to the utility companies for power grid operational. Understanding the incoming generation capacity is crucial, given that electricity cannot be stored. Maintenance a real-time balance between production and consumption is essential. Failing to achieve this balance will risk a worldwide blackout, just like the past event I mentioned about. In this slide, the solar rooftop potential for a small town has been examined using remote sensing images and geographic information. Factors such as size, angle, orientation, and location of the rooftops, along with meteorological data and solar radiation statistics, are examined to determine the upper limit of solar deployment on rooftops. This provides insights into the potential solar electricity generation capacity of province all over the whole country. In the meantime, by analyzing monthly remote sensing images along with relevant geographic information, we can effectively monitor the entire life cycle of electrical power infrastructure projects, covering the planning, construction, and evaluation phases to ensure alignment with established schedules. This example illustrates the progressive development of a substation from initial planning to full operation. The idea of the power map can be understood as the comprehensive digital duplication of power grid. It acts like a map resource and a digital representation of the actual power grid. This unified grid visualization program offers geography tools for different operational systems utilized by power grid operators. Here are two practical examples that demonstrates its implementation. Transmission lines being the most widely used and the most susceptible power facility to environmental factors requires a careful and consistent approach to their management. One of the primary duties of maintenance personnel is to conduct routine line inspections, especially occurring once each day. This slide outlines a system specifically designed for power transmission line management. This system combines various information cells, including satellite, drones, cameras, and sensors to assess environmental issues in the surrounding area. When potential risks are identified, it sends out alerts and automatically assigns inspection tasks. These assignments are transferred from the web application to the mobile device of the field workers. Once the maintenance staff receive work tasks, they proceed to the site to solve the issues. By the way, the app will also provide a navigation assistant to the mission location and enables on-site reporting features. Essentially, we leverage geographic information to improve and streamline the maintenance of power grids by merging mobile applications with online platforms. In the meantime, by using precise geographic information, this system is capable of remotely controlling drone nests and cameras based on provided coordinates. For instance, when evaluating scenarios that present hazards and need additional confirmation, the system automatically identifies the nearest drones data and to send the request task. Once they are launched, the drones are able to collect a real-time picture regarding the conditions of the area, which not only alleviates the routine responsibility of maintenance personnel, but also facilitates streamlined operations. Another example is the power meteorological system, which is also enhanced by Power Map. For instance, in February 2024, a severe cold wave swept through the entire Jiangsu province, causing icing and galloping problems with hundreds of transmission lines. This situation posed a serious risk to the rescue and reliability and management of the power grid. In the past, gaining real-time access to on-site conditions and line failure information during such severe extreme weather, it was quite challenging. However, with the help of this system, it became possible to conduct a real-time analysis of the impact of the disaster on the grid. As time goes on and more information accumulated, we utilize graphic data, power grid failure information, and meteorological data to create a range of thermal maps. This colorful map illustrates the possibility of lightning strikes affecting power grid of Jiangsu province. This process provides crucial guidelines for the selecting location for new power projects and adding protective accessories for the existing infrastructure. As we can see, this is something that electric power operating companies or public service companies in every country are currently doing or will undertake in the near future. However, because of the wide range of power equipment and the diverse voltage levels, there remains no unified geographic information standard for power equipment management. Therefore, if possible, we would like to put our efforts into this job. That's all for my speech. Thank you for your attention.
Thank you very much indeed. Yeah, really interesting. I can see the evolution from simply capturing geospatial data to map the network. Then you've moved from that to monitoring the network with IoT devices. And I suppose the next step is actually doing prediction work, to make sure that the system is resilient. A huge amount of geospatial data going in there from lots of different sources. So yeah, thank you very much indeed. Does anybody have any questions at all on that? No? Okay, thank you. Right. The only thing that remains for me then is a round of thank yous. So the first group of people I'd like to thank is our speakers who have been brilliant today. Thank you. And then obviously our sponsors and our host here at Wuhan University. So thank you very much to them. Thank you. And my final note is really, I hope you're inspired by some of this, because there was everything. There was something in there for everybody, whether it was the last bit on power or whether there was a metadata discussion earlier on. Geospatial data is heading upwards, and where the future will take us is in our hands. So thank you everyone indeed for today, and if you're going to the dinner this evening, do come along and say hello and we'll have a chat. Okay, thank you very much.